Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. In the past, we discussed the single degree of freedom system followed by a 2 degree of freedom system and explored the method of finding out the natural frequencies, mode shapes and the forced vibration response, but we essentially limited ourselves in considering fewer degrees of freedom, maybe 2 or at the most 3 in some cases. But obviously, in practical systems the degrees of freedom are many, and in that case the size of the governing equations of motion, and if you are converting that into an matrix equations of motion, that is going to be much bigger in size, and the solution of such equations can be challenging. And it is also time consuming for the systems which will have obviously coupled governing equations of motion. In today's lecture, we are going to understand how a modal analysis approach to solving multi-degree of freedom system through a much more elegant and computationally efficient way can be implemented for solving a large degree of freedom system. Before the modal analysis approach is discussed, we shall also explore the orthogonality property of the eigenvectors. Okay, now this multi degree of freedom system will be discussed for a number of degrees more than 2 or maybe even 3 for a practical system. So, I am bringing back again the physical system like a motorbike here, wherein we have earlier modeled it like a simple single degree of freedom system, where the stiffness of the suspension was found to be an equivalent one considering both the suspensions, and the chassis mass and the rider mass was lumped like a single mass having only 1 degree of freedom. That is how we started the whole the analysis process of a system like this. Later on we discussed that for a car, an automotive which has maybe a different suspension characteristic, and to also look at other degrees of freedom which could be important. So, this kind of a pitch motion, this kind of a bounce or a heave motion, we included now in that case an additional tilt degree of freedom, the theta, and the angular degree of freedom or angular motion theta, and the heave motion or a bounce motion like y. And later on in the previous topic of transmissibility, we looked at what things can change if we include another degree of freedom, that is a horizontal motion. Now, all these 3 degrees of freedom in a planar vibration are important, and they give rise to interesting additional natural frequencies. So, when we want to have all the vibratory characteristic to be captured, it makes sense many times to have good number of degrees of freedom, not too many, depending upon the physical system at hand and what is the purpose of your analysis. So, this is how many degrees of freedom can add up, and then your system now becomes a truly multi degree of freedom system. We started with only 2 degrees of freedom for the initial case, where we saw that two masses connected by springs, and let us say in the case of an anvil and a forging hammer, we modeled it like 2 mass system separated by these mounts. So, so there were only 2 degrees of freedom, then we also looked at 3 degree of freedom system, but gradually we now need to look at what happens when there are several degrees of freedom. Okay. Well, the actual process would probably remain the same for finite degrees of freedom, is to follow 2 routes. the two routes that we discussed for getting the governing equation of motion is by using Newton's second law of motion, and the other one is energy method, where you can apply Lagrangian dynamics to get the governing equations of motion. So, by writing kinetic and potential energy expressions for this vibratory system. So, let us see what happens. As I said, we initially had only bounce and pitch motion, then we looked at how the automobile or a motorbike here can be modeled by adding the wheel mass, and each wheel itself can have translatory degrees of freedom, and this chassis can have a pitch motion and a heave motion. You can also have lateral, if you consider these to be two wheels, then you can have sideways lateral motion as well. So, instead of a single resonance which you can obtain if you consider only 1 degree of freedom, you can have several such resonances when you increase the number of degrees of freedom. So, that is what is going to be obvious character of a multi degree of freedom system. You get to see multiple resonances, and so it is important to know these frequencies accurately, so that you can use your operating speed range reasonably away from the major resonances. Okay. So, therefore, eigenvalue analysis or finding natural frequencies is the first step to in the design process. Okay, so now that that automobile with the chassis mass given as m1, mass moment of inertia I, the wheel masses as m2 and m3. Now we can model this with more degrees of freedom. So, the chassis mass is now assumed to have both the vertical heave motion, and y1 is typically in vehicle dynamics is called as a surge motion. This is heave, vertical bounce motion, and the individual wheels themselves will have a vertical motion, right. So, normally a two wheeler is sufficient to consider only the vertical degree of freedom for the wheel mass. They are unlikely to have the kind of roll motion or a pitch motion that we have for a chassis body. Okay. They being a concentrated or a small sized wheels, typically they are likely to only have a bounce motion, and therefore, the 2 degrees of freedom that we are now going to use for the wheels are only the vertical translatory motion, and for the chassis not only the vertical vibratory motion, but the surge motion y1 along the axis of the vehicle, right. So, this is another degree of freedom that we are including. Now, these two and with theta as the additional pitch degree of freedom for the chassis mass, these three are the 3 degrees of freedom for the chassis, and then 2 more degrees of freedom for the wheels. That basically suffices to capture the dynamics of this particular system. Now, what we are also going to make use of are the damping property of the dashpot or the suspension, defined by a damping coefficient C1 in the vertical direction, the suspension stiffness K1 for in the vertical direction. Similarly, K2 and C2 are the damping coefficients of the front suspension. K3 and K4 now quantify the tire stiffness, because from the wheel mass the ground is separated through the compliance of the tire. So, based on the tire characteristics and the air pressure, it will have its own stiffness. In general, this stiffness is going to be nonlinear, but for the sake of initial level analysis, it will be considered a constant stiffness K4. and K3. Now, for the surge motion to happen, we can consider the lateral stiffness of the suspension, and that is given as, sorry, this has to be K2 dash. So, K1 dash and K2 dash are horizontal or lateral stiffness of the suspension, and rest of the details are all given, that the CG is located at a distance of L1 from the rear part and L2 from the front part. The position of the connection point of the suspension from the CG is defined by a distance A. Partly these all these dimensional details are quite similar to the transmissibility discussion that we had in a couple of sessions back. Okay. Now, with this, now we are set to look at what would be the way to get the governing equation of motion, and as we usually do, extract a free body diagram for individual inertia elements. So, here what we can see is that theta and theta double dot, these are the angular motion and its second time derivative. Theta double dot counterclockwise, x1 and x1 double dot, these are the motions of the mass in the vertical direction, and similarly y1 and y1 double dot. So, those are the two those are the 3 degrees of freedom that we have here. Now, obviously, for applying Newton's law, we need to figure out what is their correct connection with the surrounding and how much what are the forces which act on this free body. So, when you do that, these are all the forces which act. For example, the restoring force because of the suspension connection here would be K1 into x1 minus x2 minus L1 theta. This is the net stretch in the spring in the vertical direction, and partly this the discussion related to this restoring force, how it has come, is quite similar to what we discussed earlier in the multi-degree of freedom transmissibility case. So, I will not spend time on discussing each and every force element here, which you can figure out whether that is correct or not. So, if we assume this free body to be moving, it would be moving in its positive direction of all the degrees of freedom, and when it moves from its original mean equilibrium position, what are the displacements in the connection springs as well as dashpots is something which you can find out yourself, and that is something which will give you the restoring forces at both these two connection points from the two suspensions, as well as the dissipating forces generated in the dashpot of the suspension. So, all these forces are because of the vertical stiffness and vertical damping, which is K1 C1 and K2 C2 at the two connection points or at the two suspension locations. In addition, as we discussed that a suspension is physically shown like this, it not only has this vertical stiffness K, maybe if I can call this as Kx, but it will also resist any lateral motion. So, that resistance to this lateral motion is going to be quantified through Ky or the stiffness in the horizontal direction, which in this particular case has been defined as K1 dash and K2 dash. Okay. So, the suspension could be like this at certain angle, and then the damping will also be in parallel to it. All of that will generate both horizontal and vertical components of it. Now, these having quantified as K1 and K1 dash, K2 and K2 dash, whenever there is a horizontal y motion that happens, the forces in the horizontal or y direction at the point of connection of the spring or suspension is given by this relationship, which is K1 dash into y1 plus a theta. Because of that tilt motion, this is the net stretch in the spring, multiplied by the spring constant gives the force. Similar force will be generated corresponding to the dashpot velocities, and that is how y1 dot plus a theta dot, these are all the forces which will get generated. Okay, the similar force will be generated here. Now, having obtained these forces acting on the free body, now you can actually generate the governing equation by applying Newton's law. So, if you look at all the vertical forces or a vertical motion, mass times acceleration will be summation of all the forces in the direction of acceleration in the vertical direction. If you use this, you will get this expression, which basically is going to be the governing equation of motion for the degree of freedom x1. On similar lines, you can also look at the motion of this free body or a chassis in the y direction. So, y1 double dash will be summation of all horizontal forces acting on the mass. So, if you do that, this is what the equation you get, and now you can use the same free body diagram to get the forces acting or the moments acting on the mass about its CG, and then when you take or apply similar similarly the second law. So, m about z. So, if this is z axis, the moments about z axis I theta double dot will be equal to that, and all the moments will be accounted for, and this is how you get the third equation of motion in the pitch direction. So, along theta direction, and then of course, you are left with the other two mass elements m2 and m3, and corresponding to each of these you will get the other two remaining equations, the equations describing the dynamics of mass m2 and m3, and that is how, since there are 5 degrees of freedom in this case, which are basically x1, y1, theta 1, x2 and x3, these are the 5 degrees of freedom. You expect to get 5 governing equations of motion, 1 equation each in the respective degree of freedom, and that is how you see 5 ordinary differential equations have been obtained. You can now rearrange them so that you have the equation similar to mx double dot plus cx dot plus kx equal to 0, and that is something which you can do as a further step from this point onwards. But this is how a multi degree of freedom system can be analyzed. Many times it makes sense to use the energy method. So, you define the energies associated with the velocities of the masses. So, you write kinetic energies and potential energy arising out of the strains in the flexing elements like springs here, and that can lead to similar kind of governing equations of motion. In fact, you are expected to get the same equations by application of the Lagrange's equation. Now, once you do that, instead of writing these 5 equations, I can use now a matrix form to describe the same equations. So, now I have an equation, the same equation, same set of equations written in a matrix form. Now, this matrix, obviously M matrix is going to be 5 cross 5 matrix. You can show that the response acceleration is going to be 5 cross 1. So, x1 double dot, y1 double dot, theta 1 double dot, x2 double dot and x3 double dot will make it a vector 5 cross 1 size. A damping matrix will again be 5 cross 5. The velocity response matrix will be a vector of 5 cross 1, and exactly similar here for the restoring force. Okay, and that is going to give you a force balance in a multi degree of freedom system, mx double dot plus cx dot plus kx equal to 0. For most of our vibratory system in mechanical engineering domain, by and large all the matrices are going to be symmetric matrices. and they are constant. So, they are not going to depend on time, and the only independent variable here will be time, and then x double dot x dot, these are all the response of this multi degree of freedom system. Okay. Yeah, as I mentioned, x is the response vector comprising all the 5 degrees of freedom. Now, if you arrange these equations, the mass matrix that I used in the representation of that governing equation of motion would have this form. So, as you expect, x1, then y1, and then theta, theta 1, and then x2, and then x3. So, corresponding to all the 5 degrees of freedom, there will be corresponding mass or inertia elements in the mass matrix. The stiffness matrix can be shown to have this form, and then of course, the damping matrix will have this form. And now, what we do is we take an example where some numerical values are assumed of a typical motorbike. The vehicle's mass is assumed as 240 kgs, and some of the other details like the suspension stiffness and the damping and the other geometric parameters are all approximated as shown here in this table. If you use this these numeric values in the matrices, you will get some numeric matrix, the mass matrix and stiffness matrix in the form as you see here. Their values are shown here. So, you can use these and then figure it out yourself, that in the elements of the various matrices turn out to be as you see here in this form. Now, you can use any of the numerical methods that you might have learned in your engineering mathematics course to get the eigenvalues, okay, from these matrices to get the natural frequency expression or natural frequency values. So, ultimately this is your governing equation of motion, and it needs to be solved for natural frequencies. Typically, when we looked at a simple single degree of freedom system, free vibration governing equation of motion, your equation of motion finally in a standard form turns out to be like this, where omega n is square root of k over m. So, for a single degree of freedom system, natural frequency straight away can be obtained. For coupled pitching and bounce motion of a car body, we discussed that if they are decoupled, you can very easily get straightforward natural frequencies in pure pitching and pure bouncing mode. So, all of that is fine, but when you have many degrees of freedom, you have to solve the matrix equation, and there are standard numerical approaches to get the eigenvalues from this equation. So, one other way of getting the eigenvalues is to use standard commercial software, which we will discuss shortly. But if this is your matrix equation, and if you for the time being assume the damping to be absent, and there is a reason why in mechanical systems many times it makes sense to for the time being ignore damping to start with, and the reason is that we know that the damping does not really influence the natural frequency so significantly. Okay. If you notice the for the single degree of freedom system, what is the expression of our natural frequency? It is omega n square root of 1 minus zeta square. Okay. Now, zeta typically for mechanical systems, unless you intentionally put a very heavy viscous damper, most of the times if it is a structural damping or even damping using a dashpot, zeta is going to be fraction, and the square of that fraction and then square root of that whole number is all going to be indicative of the fact that omega d is very close to omega n, quite close. And another important aspect is that there are two things that you will get by solving this as an eigenvalue problem. One is that you will get eigenvalues, and then other one is what you know now is that there are mode shapes corresponding to each of the eigenvalue. Now, mode shapes are not going to be influenced so much by the presence of the damping. So, the mode shapes of undamped system and damped system are more or less identical. So, that is the reason why preliminary analysis can be comfortably done, and we are doing this also for the reason of understanding few other things related to multi-degree of freedom system. So, let us assume or ignore damping equal to ignore the damping or set it to 0, then your governing equation becomes mx double dot plus kx equal to 0. Okay. Then all of us are aware that either you assume the solution to be x a e to the power nu t, you can use that exponential quantity as a assumed solution, or if you are sure that it is going to be an oscillatory system, comfortably you can use the assumed solution to be x equal to capital X cos p t. That is what we have done in the 2 or 3 degree of freedom system as well. Now, if you substitute for x double dot and x into the governing equation, the matrix equation here, you can definitely show that the equation simplifies to this, and so either the matrix here is either this is 0 or this is 0. For a non-trivial solution, we equate the matrix to 0. And the equation is brought in a standard eigenvalue problem format. So, it is capital K x equal to p squared m x, that is the standard form of the eigenvalue problem, okay, which can be rearranged in this form. So, what we do here is multiply throughout by the inverse of the mass matrix, and take both the terms on the left hand side, and this is how the equation of motion now transforms, where D is equal to inverse of the mass matrix times the stiffness matrix, and is usually called as a dynamic matrix. And so, this is a standard form of the eigenvalue problem, and by a solution of this equation you get a set of eigenvalues and the corresponding eigenvectors. This capital X, what you see here is this capital X is a matrix containing all the eigenvectors. Now, this eigenvector corresponds to this particular natural frequency. The natural frequencies that you get, or the squared natural frequencies, are your eigenvalues arranged in the diagonal elements of this matrix, and the matrix of eigenvectors are in the form of vectors which are individual eigenvector corresponding to a given eigenvalue. So, for example, the first column actually represents the eigenvector or mode shape corresponding to the first natural frequency p1. The second column represents the mode shape or eigenvector corresponding to the second natural frequency, and so on. So, if you have n degrees of freedom, you will have n natural frequencies and you will have n eigenvectors or n mode shapes of the system. So, this is how a multi-degree of freedom system gets formulated as in terms of a matrix equation. It becomes more appropriate to get them represented in the form of matrices. Each individual matrix will have the elements depending upon the parameters of the vibratory system, like the masses and the stiffnesses of different elements. Now, as I mentioned to you, you can use numeric methods, you can have your own function written in any of the languages. So, here we would use MATLAB standard library functions, and the function that is used is EIG, that is for getting the eigenvalues. to which we use the inputs as the stiffness and mass matrices, and what this function will return in return is the corresponding eigenvalues and eigenvectors. So, these are all what you will get from invoking this standard library function EIG. What you need to input for this is the stiffness and mass matrices. Depending upon the size of your system, the matrix size could be n cross n, but once you substitute all the numeric values, you can supply or you can send these stiffness and mass matrices to the function, and in return it will yield you the eigenvalues. Now, these eigenvalues are, as I said, arranged in the diagonal form. So, you will have this eigenvalue matrix to have non-zero diagonal elements, and all other diagonal elements will be non-zero, and off diagonal terms will all be zeros, and these are basically the squared natural frequencies. So, if I want to find out all the natural frequencies of this particular system in cycles per second or hertz, then I can use this expression to get all the diagonal elements extracted, and because they will be given in the form of a complex quantity. For undamped system, we are going to get pure imaginary quantities. You remember that the roots S1 and S2 that you got for a single degree of freedom system were basically plus minus j omega n. So, if we want to know the natural frequency, it is the imaginary part of the eigenvalue. And so, if you get that from this particular diagonal of the matrix, you will have to take a square root of it to get the appropriate eigenvalue, right. So, when you do that, you can get all the natural frequencies of the system. So, this is now we are getting into the numeric analysis, because solving such matrix or getting 10th order polynomial as a characteristic equation is going to be a too complex and too laborious process. So, as a general approach of working with many degrees of freedom, up to 3 or 4 you can still manage, but as the number of degrees add up, it becomes unmanageable to resort to our classical approach of getting the polynomial equation. So, this is how for the vehicle case, where we had a 5 degree of freedom system, the eigenvector matrix, the first part of the solution is going to be a matrix something which will look like this actually, and eigenvalues would look like a diagonal matrix, a matrix having non-zero diagonal elements, and then if you extract all the diagonal elements, take the square root of it, these are all the 5 eigen or natural frequencies that you will observe. Okay. And so, now corresponding to this eigenvalue or this natural frequency, the mode shape is going to be looking like this. This is going to be your first mode shape, not necessarily first mode shape. I would say that the mode shape which is there in the first column here is corresponding to this natural frequency, and so on. Okay. Now, if we ignore the mass of the wheel, okay, for this system what we are now going to look at is what happens if we simplify the model. So, in place of using these additional x2 and x3 degrees of freedom, if we use only these 3 degrees of freedom of the vehicle, then the mass matrix is this, the stiffness matrix turns out to be this, and then using the same command, except that the matrix size are reduced, you get the eigenvectors as these 3 eigenvectors, and these are the 3 eigen values or the natural frequencies of the system. So, please remember that these numbers are actually cycles per second. So, they have been converted by dividing by 2 pi from the otherwise the standard unit for the frequency is radians per second, just for the sake of representing the values. So, that hertz is a common frequency unit that is used in practice, but for all mathematical purposes and standard expressions or equations that we have should give you the natural frequency in radians per second. Now, what does what do these two results tell us? That if we use all the 5 degrees of freedom in the system, and when you use just 3 degrees of freedom ignoring the wheel mass, that is what we have been doing in the past, that we ignored the wheel mass and then we kept the degrees of freedom as low as possible. The existing problem that we have discussed with 5 degrees of freedom are just to make the evaluation more accurate, so that the contribution of the individual wheels are also included in the analysis. But in terms of the natural frequencies, you can notice here that the first 3 natural frequencies that you obtain are quite comparable to the 3 natural frequencies that you obtain by ignoring the wheels. See this? Just compare these two set of natural frequencies. Using 5 degree of freedom, if I focus only on these, ignoring the higher 2 natural frequencies here, that is what you get, and they are quite similar. So, if you calculate the percentage error is maximum 5% error, and that is reasonable, okay, because all of this analysis is done to have a preliminary guess and some idea about what natural frequencies are. And if you are usually we are more concerned about the initial few eigenvalues or natural frequencies. The higher eigenvalues are not always essential to find. Now, we have discussed this in terms of that winch problem, where the higher natural frequency is far apart from the normal lower natural frequency, and so it depends upon what frequencies are excited to this system. If the excitation to this system is lower than, let us say, 3, 4, 5 hertz, let us say, okay. So, then these frequencies may not really influence the total dynamic response, okay. Higher mode frequencies do not contribute as much to the response if the excitation frequency is close to some of these lower natural frequencies, okay. Now, if you plot this graph of natural frequencies, all these natural frequencies will be close enough here, the third one will be there, and you can see that the fourth one and the fifth one, they are very close. Of course, they are lying in higher frequency range, okay. So, most of your first few natural frequencies are going to be of course corresponding to the numeric values which we have chosen in this particular vehicle model, but trust us that these values are not very imaginary in that sense, in the sense that they are the values taken are realistic values of a typical motorbike, okay, taken from some source. So, these values are realistic values of the tire and the chassis, and also the suspension stiffnesses. And what you are observing is that it suffices to use lesser degrees of freedom, and the error in the estimation of the natural frequencies with the fewer degrees of freedom is not substantial actually. So, you can actually use as low number of degrees of freedom as you wish. The only thing that will happen, that suppose these wheels have now the some of the wheels will have their own unbalances, no. So, when unbalance is there in the wheels, you would like to know what is the allowable unbalance that I can tolerate, which generates sizable response in the chassis, okay. So, then if I am interested in analyzing the response to wheel unbalance, then maybe wheel mass can be included. It is not that you cannot find this out by not including the mass of the wheels, but if you include the wheel mass and then apply the forces here at this degree of freedom, then you can find out what is the response or influence of that unbalance on the response of the chassis. Okay. So, all of these considerations decide also the degrees of freedom that you need to account for. Okay. So, therefore, it is always said that your first step of capturing the physical system as a simplified vibratory model is governed by your own experience of what the system is all about. Your target, your final goal or target of your analysis process, what exactly you want at the end of the analysis, that will decide how complicated or how simplified the model you make out of the physical system. Okay, now a little bit of discussion here about what it basically tells you from the mode shape. Now, these are not going to show you a mode shape in a very nice way, but supposing we look at this mode shape, okay, and then these degrees of freedom are like x1, y1 and theta, then the lowest mode here is showing that if the mass moves 1 unit in the y direction, that means there is a surge motion of this chassis horizontally, there is a strong theta motion that happens. Okay. So, we can expect physically, you can see that if the surge takes place along the direction of motion of the vehicle, it is natural to expect a pitch to happen, and that is happening here, because in this case non-zero value of this theta actually means in the mode shapes. These are all mode shapes, right. I hope you recall that we discussed the mode shapes of a simple 2 degree of freedom system for one particular case when there were two masses connected like this, right. You remember that a spring here was K, this was K, this was 2K, this was M and this was M. So, what was the first mode? The first mode was defined like this. There were both the masses were moving with the same amplitude in the same direction. That was your first mode 1 1. In the second mode, I hope you recollect that in the second mode this was the way the mode shape was, 1 unit of mass m1 in the opposite direction the second mass moved, right. So, 1 minus 1 was the second mode shape. So, here you have a 3 mass or a 3 degree of freedom system. So, you will have 3 mode shapes. So, this one was the mode shape number 1, first mode, and this one was second mode. Now, here what we are getting in the first mode, mode number 1, the values are 0.05, 1.0 and minus 0.41. Okay. So, how do we visualize this? That if the body or a mass has a the surge motion in the horizontal direction, the pitch is going to be clockwise, which is opposite to the positive direction that we have assumed, which is expected. In this case, physically it is going to tilt a lot whenever there is a unit motion in the y direction that is happening. In the second mode, at some higher natural frequency, now you have a vertical bounce motion taking place. Okay. And because the CG here is not assumed to be in the center of the span as a general case, you have a coupled pitch and bounce motion possible. So, which means that if you try to lift the chassis up at the CG, it is going to also tilt, and here the CG position could be such that you still have a vertical x1 motion. If it is 1 unit amplitude, there is a little bit of a tilt in the clockwise sense that is happening. 0.02 represents the theta value. Okay. and at the same time, because theta is coupled with y1, okay, the pitch motion is coupled to the surge motion. So, you will have some horizontal motion also taking place in this case. That is how to read about what the mode shape represent in this case. And then of course, you can have a largely pitch motion, very little of bounce in this case. That is how you can interpret each of these mode shapes um, in each of the natural frequencies. Now, please make a note that these are all shapes. That means, it should not be confused that the body is going to move with 1 centimeter amplitude. That 1 centimeter can be 1 millimeter, can be 1 feet, but if it moves 1 feet, the motion of x1, okay, is fixed in relation to that. It will move with the with the same ratio, as if it is moving with 1 degree radians, this value will be in meters, and supposing if the vertical motion is 1 unit or 1 centimeter, this will be 5 millimeter. Okay, that is yeah, 50 millimeters if this is 1 meter. So, it is all 5 millimeters. So, this is all relative. So, if you have a motion in any value that is taking place, these are all relative values. So, if I have a mode shape which is saying the second mode shape, if I rewrite here as 0.05 minus 0.02, then if this is second mode, if this mode shape is for the second vibratory mode, then this also is the same second mode, this, because it still represents that the ratio between this and this motion is same as ratio between this and this motion, numeric value. So, if this x 1 is a mode shape, then n times or I times x 1 is also the first is also the mode shape, right. So, it is basically a relative displacement amplitude that we are talking about, right. So, these numbers should be viewed as the shape or a displacement pattern of the entire system, rather than the physical values representing the final vibratory response. It is not like that. And the other important thing is, each one of them corresponds to the way it vibrates when vibrating at that particular natural frequency. Okay. So, when the whole vehicle body is vibrating at 1.102 hertz natural frequency, then the individual motions of all the degrees of freedom will maintain this relationship between them. Okay. That is what it actually means. So, mode shapes correspond to the natural vibratory motion happening at a particular natural frequency. So, we have now been able to write these governing equations in this form, matrix form. So, I am rewriting this equation, sorry, this will be plus. So, this is free vibration multi degree of freedom governing equation of motion. This is basically your response vector, which is q1, q2 corresponding to each of the degrees of freedom, q1t, q2t up to qn t, which is n cross 1 vector. Okay. And as we discussed, this is mass matrix is n cross n for an n degree of freedom system. The vector of accelerations are going to be n cross 1, all of them will be n cross 1, and then these are the square matrices n cross n. All right. Now, if you recall, we discussed in a 2 degree of freedom system, general vibration response is contributed by its corresponding the contribution to the vibratory response at each degree of freedom will be contributed by all its modes. Okay. So, what I can write here is that this x1, the response of the first mass is going to be written as some arbitrary constant a1. You remember that we wrote this as cos pt or p1t minus phi 1 for a 2 degree of freedom system, and the contribution from the second mode, which is b1 cos p2t minus phi 2. And on similar lines, the mass 2 moves and its general vibratory response was given by a2 cos p1t. Again, the mass 2 also moves with a contribution coming from both the natural modes. So, p2 is the natural frequency in the second mode, p1 is the natural frequency in the first mode. You remember that a1 b1, a2 b2, phi 1 phi 2, these are all the arbitrary, these are all the constants which needs to be found from the using the initial conditions. But we also know that if the contribution comes from p1 or the first mode, the amplitudes of the first and second mass maintain some relationship, right, and that relationship is nothing but your mode shape. So, a1 by a2 by a1 was xr1, we defined this as the mode shape, and sorry, the b2 by b1 was xr2. Okay. So, if we now see this in a general one specific case of 2 mass system where the degree of freedom were 2, and then their numeric values were such that the mode shape was 1 1, then which actually means that a2 by a1 was 1 for p1 mode, and then the b2 upon b1 for the second natural frequency was minus 1. So, this mode shape was 1 minus 1. Why? Because b2 was equal to minus of b1. So, if b1 is 1, then b2 is minus 1. That is how it happens. So, this 1 is nothing but your xr1, and this minus 1 is your xr2. Okay, that is what changes this x2 equation now. X2 equation will be written as a1 times xr1 cos p1t minus phi 1 plus, so I can write that as b1 xr2 cos p2t minus phi 2. Now, I can use these two equations x1t x2t equals to a1, and I can use this 1 and xr1 as the mode shape, first mode multiplied by a1 as a constant, and then that basically is your first column. Okay, that basically is your first column here, and the second column will be b1 1 and xr2, and I can use these harmonic time functions here. Now, you all know that if 1 xr1 is the first mode or a mode shape, then any constant multiplied by that is also a mode shape. Okay. So, what I am going to do is I will write this Qt or the response of a multi-degree of freedom system, the way I can write this as a matrix which contains individual mode shapes like x1, x2 and so on, multiplied by cos p1 t, cos, just ignoring the phi which can be accounted for later, but it essentially is a matrix containing all the mode shapes of an n degree of freedom system multiplied by the harmonic time functions. So, this in a similar line I can write this Qt as a set of modal vectors. If I consider this to be n degree of freedom, then u1 u2 up to un would be these mode shapes or vector containing the relative displacement amplitudes of each degree of freedom, and then multiplied by what I will use here is a coordinate which I call as a principal coordinate or a normal coordinate, okay, eta t, which are nothing but these harmonic time functions. Now, this equation is a very powerful equation which basically defines what is known as modal analysis, wherein the physical coordinate is written in terms of principal coordinate, and this matrix contain all the modal parameters. Now, modal parameters, why? Because that matrix has the elements which are basically the mode shapes of this multi degree of freedom system. And why are we doing this? Please follow this process with patience. You will definitely realize later the power of using this transformation and how the solution process becomes so convenient, computationally convenient for solving many degrees of freedom system. Okay. Now, if we look at the governing equation of motion which I have written here, I have shown in some of the previous slides that your mass times, so this is p squared m into capital X was shown to be k times x, was it not? One of the let us say ith natural frequency squared times mass matrix times the mode shape, which is maybe ith mode shape, was shown to be this way. Okay, this was the equation that we discussed the other day, right? Now, these mode shapes follow a property called as orthogonality, okay, and we are basically going to discuss how this orthogonality property of the mode shapes can be made use of in the convenient and computationally efficient solution process. So, based on the equation that we had solved here and got this kind of an expression that we obtained, p squared m into x is equal to k into x. We will start from this particular equation where capital X is one of the mode shape or a modal vector, and p represent that particular natural frequency. Okay. So, I will rewrite this as k times, since we have been using u as these modal vectors, I shall now start using this u and I will use a subscript r to represent the rth mode shape, is equal to the natural frequency will be rth natural frequency. So, PR square times m into UR. Okay. This is what the same equation I have written slightly in a different form. Now, what I do is I will pre-multiply the entire equation by another mode shape or a vector representing sth mode shape. So, I will multiply the mode shape sth mode shape vector to this equation, and that gives me this equation. Okay. Now, the way I have got this equation, I can also get the equation when I consider the sth mode. So, if I am considering the sth mode, so when I consider the rth mode, I get this particular equation. If I use sth mode, I can write the equation to be us equal to ps square m times us, isn't it? Now, if I pre-multiply this equation by UR transpose, then the way I have got this equation number 1, I get equation number 2, which I am going to write it this way. Now, soon you will realize what are we up to. Just hold on for a while now, because it looks little weird why we are doing all of this. That is going to open up interesting things shortly. Okay. Now, as long as your matrices are symmetric, it is possible to show that these mode shapes being orthogonal, US transpose M UR is equal to UR transpose M US. This you can try on any sample example containing mass matrix or stiffness matrix. So, it is quite straightforward to show that this is true for mass and stiffness matrices. So, they being symmetry. So, UR or US transpose similarly for K matrix will also be the same way. So, you have UR is equal to UR transpose K into US. Okay. Now, we make use of this in rewriting these two equations now. So, what we are going to write here is I am going to write this equation as UR transpose K US is equal to PR square. So, I am writing this equation by invoking that relation that I have written here. Okay. So, this is one written or maybe I will write this as equation number 3, which I get by substituting this relationship in the equation number 1. Now, I will subtract 3 from 2. If I subtract equation 3 from 1, what I get? I get 0 here on the left hand side. On the right hand side, I get UR transpose M into US in bracket PS square minus PR square. Okay. Now, what does that mean? That if P sorry if R is equal to S, which means that I am talking of the same mode. Okay. When R is equal to S, PS and PR will be identical. They mean the same natural frequency. Numerically, that will mean that the bracket is 0. Okay. So, when R is equal to S, I can write that is not equal to 0, because this bracket is 0. And I can say that this is not equal to 0, but I can write that to be a quantity called MR. Okay. Now, what is MR? It is called generalized mass Rth mode generalized mass. Okay. If R is not equal to 0, if R is not equal to S, then for this equation to be true, what would it mean? Your transpose M US has to be equal to 0. Okay. And using the same in these equations, you can easily show. So, what you have shown is this. You can also show, just try it out yourself here in this equation number 3, that U R transpose K U S is not equal to 0, but is equal to K R if R is equal to S, and is equal to 0 if R is not equal to S. Okay. So, these are basically the mathematical equations representing the orthogonality of the mode shapes with mass and stiffness matrices. They result into these interesting outcome where Kr here is called as the generalized stiffness. Okay. Kr is called as the generalized stiffness in the Rth mode, similar to Mr, which is the generalized mass in the Rth mode. Now, hold on for a while. You would wonder as to how this is going to be of any use to us, in what way this is going to be of use, and trust me that sooner you will realize the potential and the utility of all these relationships that we have got here. All right. Now, if we go back to the equation, matrix equation, I am for the time being ignoring the damping matrix here. Okay. Now, the previous case where the orthogonality of mode shapes were discussed, what we got is the U R M into U S. U R and U S are basically rth mode vector representing the rth mode shape or sth mode shape. What we discussed was that this turns out to be mr for r is equal to s, okay, and this is equal to 0 when r is not equal to s. So, what we can do is these mode shapes can now be normalized. So, I am basically going to normalize the mode shapes by writing u tilde r equal to 1 by square root of mr times ur. Again, this is done with being done with a specific purpose, and you will realize that shortly. So, I am basically the way we can get 1.05, 2.31 and 0.05, this kind of a mode shape you can get. What you can do is to get it is standard practice to normalize this with respect to the displacement of 1 of the degree of freedom. So, I can keep this as 1 and then accordingly get the other numbers normalized with respect to this one, which makes more sense. But in addition to that, this process is going to yield another very important and significant impact on the solution process. So, what we are doing here is the rth mode shape is normalized by dividing in all the elements of this rth mode shape by square root of the rth mode generalized mass. Okay. So, 1 over square root of mr is going to be the normalizing factor to get all the vector quantities normalized, and the reason why we do it is going to be shortly clear to you. Now, if you do that, it is almost like dividing this particular equation throughout by mr. Okay. So, then square root of mr gets distributed in this as well as this mode shape, right. So, now I can use the same equation in the normalized modal vectors, and the normalized modal vector is represented by a tilde on top of u. So, this is ur tilde transpose times mass matrix times ur tilde us tilde is going to be equal to 1, of course. Okay. Why it is 1? Because I have divided throughout by mr, and 1 square root of mr gets absorbed in the normalized modal vector here, and the other one gets absorbed here. This is going to be very interesting equation, right. Now, on the similar lines I can do it for the stiffness matrix. So, now if I use the mass normalized modal vectors, so ur tilde transpose into k into us tilde will be how much? You recall that our equation was what? ur transpose k us was kr when r is equal to s, okay, and was equal to 0 when r was not equal to s. So, now if I divide this equation throughout by mr, which means if I divide it by mr on the left hand side and also divide this by mr on the right hand side, then this part is what I get here, because all these modal vectors are transformed to mass normalized modal vectors, which I define by or represent by tilde on u. And on the right hand side, what does this represent? It represents the rth natural squared natural frequency PR. So, PR square is KR over MR, okay, and PR square is now the rth mode natural frequency, and that is how you get these equations. Okay. Now coming back to this equation, what is our modal transformation that we defined? This was equal to individual modal vectors. Okay. So, u1 up to un and was multiplied by the principal coordinates eta t, represented by eta t. It could be eta 1, eta 2, eta 3. So, this eta is the vector containing all the principal coordinates eta 2, eta n t. This is we have this equation we have already discussed and shown how it works. Now, because these modal vectors are I mean if u1 is a modal vector, n times u1 is also a modal vector, right. So, I can use this this matrix as represented by u, and all of the elements of this matrix U are mass normalized modal vectors. Then this equation Q of t is represented by an equation like this, which is basically meaning that this modal matrix is basically containing all the mass normalized modal vectors. So, each one of them is like u tilde 1, u tilde 2 and so on up to all the n matrices. Okay, now what we do? We will now start looking at this equation and transform this equation into its into from the physical coordinate to modal coordinates or principal coordinates. So, this capital M stays as it is, but now Q I will replace. Now, the way I use Q double dot here, U is going to be your constant and eta being the time dependent harmonic functions. If I take the time derivative of eta t, I can represent that to be eta double dot t. So, now this m q double dot is now going to be replaced by eta double dot t and plus this k q t here is being replaced by so I am basically going to use this expression and its derivative to transform this equation in its these are given in the physical coordinates, you know, the degrees of freedom x1, y1, theta 1, all of these are being represented by the vector q. Okay, this is the actual physical response of the system to the coordinates which are the principal coordinates. So, they are not the physical coordinates, they are principal coordinates, and the equation of motion is now transformed into this equation of motion. Now, why are we all doing this? When you consider this equation, we know that all these equations are like in the form mx1 double dot plus k1 x minus k2 x2 and blah 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 equal to 0. There will be another equation in x2 where you will have minus k2 x2 plus k2 plus k3 into x3 and so on. The point is your governing equations of motion are all coupled equations. So, you have you know all these n number of equations, they will all be coupled. That is why you saw the matrix K where having number of off diagonal elements which are basically indicative of the fact that the equations are all coupled together. So, solving such large number of equations, differential equations, for getting the solution when they are coupled is difficult in the sense that it will take time. It takes time. It's the solution process is not straightforward. Okay. Let us now see how do we get around this problem of coupled governing equations of motion? So, now I am going to pre-multiply this equation that I have got by U transpose. Now, make a note that U is the modal matrix and I have simply pre-multiplied this . Now, what I get? U transpose means what? In this I will have your U1 transpose, is not it? The second row I will have the second row here U2 and so on, right, and I have your mass matrix here and then I have U1, U2 and so on. So, if I consider the first modal vector multiplied by mass matrix and this, it actually turns out to be this U1 transpose mass matrix, the first element of this entire. So, this product U transpose M into U, it is all going to be, all these columns are going to be like rows now. So, this is going to be U1 transpose going to get multiplied by the entire mass matrix and this is going to be all U1, U2 and so on. So, if you really work yourself from here, the first diagonal element here, okay, this diagonal element is actually going to be U1 transpose M into U1. This off diagonal element is going to be U1 transpose M into U2. This second diagonal element is going to be U2 transpose M into U2. What is this value? Because we are considering this to be mass normalized modal matrix, the product of the same modal vector with the mass matrix pre multiplication and post multiplication, this gives you a value equal to 1. This off diagonal element, what would it give? When R is not equal to S, okay, then you get the product to be 0. So, when you have two orthogonal vectors, modal vector 1 and modal vector 2, this orthogonality is now like a dot product of two vectors. When they are at 90 degrees, their dot product will be 0. Okay, if you are talking of two different vectors, independent vectors. Now, so U1 tilde or U1 transpose M multiplied by U2 is going to be 0, but if you use the same vectors, okay, same over the other, their product is not going to be 0. So, basically this is going to be 0, U1 transpose M U2 is going to be 0. In that sense, all other off diagonal elements where R is not equal to S, all those elements are going to be 0. And whenever you have the two vectors being identical or same, then the second diagonal element is going to be u2 transpose mass matrix times u2, and that is going to be equal to 1. So, you can think about it and work this out. You will realize that the entire product of u transpose mass times u is all going to be an identity matrix with all the diagonal elements being 1. So, this is going to be replaced as identity matrix, and how much will be this now. Likewise, if you work this out the way we have done for the mass matrix, it is quite straightforward to then represent here that right, you can show that if you use K matrix now, this is going to be what? Yeah, U tilde, that means mass normalized modal vector, when you multiply it with K, what do you get? PR square when R is equal to S and is equal to 0 when R is not equal to S. You got that, right? Using this, when they are mass normalized, the product gives you PR square. So, what is going to happen is that you are going to get this as P1 square, the second diagonal element as P2 square and up to Pn square, and all these off diagonal elements are going to be 0 because of the orthogonality, and that basically means that this matrix is going to be a diagonal matrix containing all the squared natural frequencies, which are basically your eigenvalues, times eta t equal to 0. That is basically is your transformed matrix equation representing this multi-degree of freedom system. The only thing is, instead of a physical coordinate like q, you are having this equation in terms of eta, the principal coordinate, the modal coordinate. Now, do you see a difference between this equation and this equation? One of the major significant difference that you have between these two equations is that your first equation is a coupled governing equation of motion. Okay. This equation is a coupled set of coupled differential equations, but if you consider each one of the equations which is represented by this matrix equation, what you have, this I, the identity matrix, which means that you have 1 1 1 in the diagonal elements, all others 0, and eta 1 double dot t, eta 2 double dot t, and so on, plus the spectral matrix is nothing but what? P1 square, P2 square, all along the diagonal, right, multiplied by again eta 1 t, eta 2 t, up to eta n t equal to 0. Now, if you remove each of these equations, just take first row, what do you get? Eta 1 double dot t plus P1 square eta 1 t equal to 0. This is going to be your first equation if you take only the first row. The second row will give you what? Eta 2 double dot t plus P2 square eta 2 t equal to 0, and so on. So, what this transformation has done for you, is that from an n coupled differential equations, you have got now n uncoupled equations of motion, and each of these equation is like a single degree of freedom governing equation of motion. Do you see that? X double dot plus omega n square x equal to 0. Okay. What is the advantage of these equations? You have standard solution available for this, right? But do you have standard solution available for such kind of a coupled multi degree of freedom system? You do not. Think about multiple degrees of freedom means think about hundreds of them, right? But you have a standard format for all the 100 equations. You don't have to look further. I mean, this is all what we have already learned in the single degree of freedom analysis. So, in nutshell, now you should be able to connect all the dots. You have been wondering as to why we are doing all of this, right? Why we are writing this kind of equations where the orthogonality was discussed, why we are transforming to this kind of a transformation from physical to modal coordinates. All of that makes sense the moment you get to see the final result here, which shows all your coupled differential equations of n number of such equations. Suddenly you see that they are all getting converted into n single degree of freedom system equations of motion, which are quite similar to a single degree of freedom system. In fact, each one of them represents the motion that is taking place in that particular modal coordinate eta 1. The moment you write the solution eta 1, eta 2, eta 3, which you know now how to get, you can plug it back into this transformation, right. So, once you solve it for eta, you basically know this vector completely. You already know this modal matrix, because what is modal matrix? It is ultimately coming out of the eigenvalue analysis. So, this is something which is known for your system, right. The moment you do that, you get the physical response, because you are not interested in getting the response in principal coordinates. You are interested in knowing how much is the motion of the physical system, that is x and y and theta, right. So, the objective now, or the next step now for us, having shown that the power of the modal transformation and the orthogonality property is to decouple all these governing equations of motion, so that you get a set of ordinary differential equation in only one coordinate, decoupling it with all the others. You can solve it and then plug it back through the same transformation to get the physical response. Okay. So, that is the power of this transformation that we discussed. Okay. Essentially, the whole purpose was to decouple all your governing equations of motion. Once you decouple it, your standard expressions for a single degree of freedom system will simply suffice, and that is what we shall discuss, how to make use of what we learned for a single degree of freedom system to solve this multi degree of freedom system. And I hope now you are able to realize and the importance of studying the single degree of freedom system. Multi degree of freedom system is something which there is nothing great in it, because all what you learned, all the basics of the first single degree of freedom system will now get implemented for arriving at the solutions. Summary of this lecture: we discussed the orthogonality property of eigenvectors, in which the eigenvectors, how they are orthogonal with respect to stiffness and mass matrices was discussed. In addition, we got introduced to the solution approach, understood how the coupled governing equations of motion actually get decoupled by using the modal matrix and the orthogonality property, which actually is the foundation for an efficient calculation of finding out the response of a multi degree of freedom system. These are the review questions that you can attempt, and these are the answers.